All right, the last concept in this unit is empirical and molecular formulas. Now, what we're really doing here is the last lecture, we looked at taking a formula and doing a percent composition. Well, here what we're going to do is exactly the opposite. We're going to take the percent composition and work backwards to figure out what the formula is. And that's the technique we're going to utilize. It involves a series of steps, but again, just like all the other stuff in this unit, it can be really easy if you do enough practice on it because it is a procedural step. You do this first, then you do this, and you do this. As long as you do your math right, and they're all simply multiplying or dividing types of concepts, you should be able to get and apply this to any single problem. It doesn't matter what the empirical form problem will be, what the chemical compound is, it's the same exact series of steps. Now, what's the difference between a molecular and empirical formula? The molecular formula is the actual formula of the chemical compound. For example, butane. Okay, if you have a butane lighter, the chemical compound inside of that is C4H10. But its empirical formula would be its simplest whole number ratio. For that, we can see that they're both divisible, the subscripts are divisible by 2, and so we can get C2H5. This is the simplest whole number ratio for this chemical formula. This is the empirical formula of the chemical compound butane. However, it's not the true chemical formula, and that involves then a series of steps to be able to first get to the empirical and then be able to translate that into the molecular. And that's what these problems are going to look at. One side note, for an ionic compound, the empirical formula is always the chemical compound because by definition, we want the simplest whole number ratio. So for example, when I've got tin 4 oxide, if I were to cross drop, I get SN2O4, but as we did ionic compound formulas, we always said that when we cross drop, if we can reduce the formulas, we need to, and therefore the real formula is SnO2. This is the empirical formula, but it's also the true chemical formula for tin 4 oxide. Okay? So for ionic compounds, we always reduce, and therefore that is the true chemical formula. But for molecules, because of how they bond, if I were to try to draw the Lewis structure for C2H5, you'll notice that we can't even make the chemical formula C2H5 because it doesn't follow the octet rule. We need to have the full number of carbon and hydrogen molecules and now we have the chemical formula. So with molecular formulas, it's because of the sharing of electrons that the formula, the molecular formula, may be a ratio of atoms that is not the simplest whole number, but that's due to how they're bonded in the structure of the chemical compound. Okay? All right, the steps to the process are here, but I think it's just a lot easier for me to go through an example problem and show you what to do. If you are given the percentages of each element, we have been given the percent composition. The first step we need to do is convert the percentage and get it into grams. And the way that we do that is we assume that we have a 100 gram sample. Therefore, if I have 11.2% of 100, that gives me 11.2 grams of hydrogen and 88.8 grams of oxygen. What we literally do is just cross off the percentage symbol and we put down a G. The next step is to convert the grams of each element into their moles. And we can do a mass to mole problem. Last week we learned how to do a mass to mole problem, and that is using the molar mass, or if it's an element, the molar mass of the chemical compound. 1 mole of hydrogen, if I look at the atomic mass of hydrogen, 1 mole of hydrogen will weigh 1.01 grams. 1 mole of oxygen will weigh 16.00. Remember, the masses on the periodic table are not diatomic. They're single monatomic masses. And that's what we want to utilize always for empirical formulas, because diatomic formulas are only when we have the chemical compound. And these are elements within a compound, so we always use just the masses from the periodic table. Okay, so we go ahead and divide. Now what I tell students to do is to write down at least 4 decimal places. The more decimal places you use, the better the final answer will be to the whole number that we're looking for. This one just so happens to come out to being only 2 decimal places, even. So we have 11.0891 moles of hydrogen to 5.55 moles of oxygen. Now technically that would be the ratio of this chemical compound, H 11.0891, 5.55, but we want the whole number ratio. So now what we got to do is take these mole quantities and we identify the smallest mole quantity. If I've got 10 elements here, I find the smallest mole quantity of the 10 elements and I divide all of them by that number to get this into a whole number. If I divide 5.55 by itself, I get 1. And now if I take 11.0891 divided by 5.55, we get 1.998. And just because of rounding, this number you can see is really close, so close that we can just simply say that due to rounding situations that this is a 2. What these are now are the subscripts. So the chemical compound is H2O. So that's how we take the chemical assay and work backwards to get the chemical formula. All right, go ahead now and try to do the same exact steps for this element that contains carbon and hydrogen. Go ahead and give it a try. All right, looks like you should get the chemical compound for methane, C1H4. So again, we took each of the masses, we converted the percentages to grams, divided by each element by its atomic weight, and then identified that the 6.2 was the smallest mole quantity, divided by both, and we get 3.964, which is really close. And we get numbers this close, we round them, and we have a value of 4. So we get the formula 1 to 4, methane. Okay, let's turn the page. Example that is butane. Butane's empirical formula, as we'd already saw, was C2H5. That was the lowest whole number ratio, but neither the carbon or the hydrogen has a 1 in front of it, as a 1 for a subscript. So this 2, when I do this technique, I'm going to get 1 for carbon, and I'm going to get 2.5 for hydrogen. This is the formula that I'm going to get when I utilize this technique, because the small subscript is going to be a 1. So then I've got to figure out how to get that into the empirical formula, and then that might still not even be the true formula, where I have to then figure out its molecular formula. To be worried about are right here. You have to be worried about halves, thirds, and fourths. Don't worry so much about fifths. I'm not going to give you fifths at all this year. So worry about halves, thirds, and fourths. So 1/3, 2/3, okay, 1/4, 3/4, halves, all those are the possible fractions. So these are the fractions you need to be concerned about. Empirical formulas where they come out to whole numbers right away. All right, now let's go ahead and do problem 3. Again, I'm going to pause the lecture, give you a chance to go ahead and do this and see what we come up with. This one involves another additional step, but I wanted you to at least get started to getting to the empirical formula. So give it a try. All right, so if you do the first couple of steps, we now get 1 for carbon and 2.66 for hydrogen. Now, this number is not anywhere near 3. If we're within like 0.1, we can round, but anything beyond that, it's too far away from that. The problem with the technique that we are utilizing is the assumption that in the chemical formula, that one of the chemical, the subscripts is a 1. That's what this technique is utilizing. Now in a chemical compound like up here, X2Y3OZ2, the technique that we're going to utilize is actually going to give us 1X, 1.5Y, and 1Z, because it's going to reduce this ratio down so that the smallest number is not a 2 but a 1, we're going to get a fraction. Same thing happens here. So right away, when I don't get whole numbers for both my numbers, what that tells me is that the empirical formula does not have a 1 as one of the subscripts. In this one, we have 1 carbon and 2.66, which is what fraction? This is where you got to know fractions. 0.66 is roughly 2/3. So 2.66 is 2 2/3. Right, now, why is it important to know the fraction? Because we do have the correct ratio. The ratio of 1 to 2 2/3 is the correct ratio of the elements. It's just not the simplest whole number ratio. So how do we get it to the simplest whole number ratio? We multiply all of the subscripts by the denominator of the fraction. So we are going to multiply both the carbon and the hydrogen by 3. So 1 times 3 is 3, and 2 2/3 times 3 gives me 8. The empirical formula is C3H8. Okay? Now, can this formula reduce down to 1 2/3? Well, if I were to divide both of these by 3, 3 divided by 3 is 1, and 8/3 reduces down to 2 2/3. So yes, indeed, this is the empirical formula, C3H8. Okay, but again, the problem with this technique is the assumption is that a subscript is 1, and when it's not, you will get fractions. Now, the fraction, you do these problems. Okay? All right, pause the lecture now and do the next one. Number 4 is very similar to number 3, and see if you can figure out the empirical formula for this iron-oxygen compound. All right. You can see the math, converting the grams of iron to moles, to oxygen moles. The smallest mole quantity of the two is 1.2963. Dividing both of them by that number, we get 1 and we get 1.33. And 0.33 is 1 1/3. So now we're going to multiply both subscripts by 3, and we get Fe3O4. That is the empirical formula of this chemical compound. Okay? All right, now, we've been doing, these are all examples of empirical formulas. So, and empirical formulas where we end up getting a fraction. And then we have to convert into the simplest whole number ratio. Now, what happens if the chemical compound, its molecular formula, does not match the empirical formula? Well, the great thing is this. The first step is to find the empirical formula. So do exactly what we have been doing. All right? Then we need to be given another piece of information, which is the molecular mass. If the molar mass of the compound does not match the empirical formula, you then have to figure out how many times bigger the empirical formula has to be to equal the molecular mass of the compound. All right? So I'm going to show you how to do that in a problem like this. All right, so we have 80% carbon. Whoops. So right away I convert that to grams. 80 grams of carbon, 20 grams of hydrogen. Dividing each of these by their molar masses. So 80 divided by 12.01, 6.6611, and 20 divided by 1.01, 19.8020. We're going to divide each of these by the smallest number. And we get 2.97, and that is definitely close enough to say that that's 3. So we get the empirical formula CH3. All right, now this is the empirical formula. Is it the molecular formula? How do we know? The next step is we figure out the molar mass of the empirical formula. Okay, so we have 1 carbon and we have 3 hydrogens. Adding those together, we get an atomic weight of 15.04 grams. The molar mass of the compound was given in the problem. The molar mass of the compound is 30 grams per mole. So we can see that the empirical mass of the compound does not match the molecular mass. Now, one key thing, the mass could match, but what will never happen is the empirical mass should ever be bigger than the molar mass, because the molecular formula should have a higher ratio than the empirical formula should have. So now what we do is we divide 30 by 15, and you guys can probably already see this. We have the right ratio. The ratio of 1 to 3 is the correct ratio. It just needs to be magnified by a number. Well, CH3 adds to 15. The molecular mass of the compound is 30. We need to make this, if I divide this, it needs to be 2 times heavier. And how do we do that? We keep the same ratio, but we have to make it twice as heavy by doubling all of these subscripts. So the chemical compound for this compound is C2H6. A couple quick checks. Does this reduce down to the empirical formula given? Yes. If I divide both of them by 2, I have a ratio of 1 to 3, which is the empirical formula. If I add up the weight of 2 carbons and 6 hydrogens, what do I get? I get a molar mass of around 30 grams per mole. So both of those check out. The chemical formula reduces down to the empirical formula that we found out, and its molecular weight does match the molecular mass of the compound. We are good to go. So once we figure out the empirical formula, we find its mass. We then divide the molar mass given in the problem by what the mass of the empirical formula is. If it matches, the empirical formula is the molecular formula. If it doesn't match, you should get a number, a whole number multiplier, which then we multiply to get the true molecular formula. All right? Okay, so let's go and do the last problem now. I'd like you to go ahead and read through this problem and see if you can figure it out. It involves a little more depth and detail, but give it a try first, and then if you get stuck or if you get through the problem, start the lecture up and I will show you the work for this entire problem. All right, the first part of the problem that was a little bit different is they actually gave you an analysis in which they immediately gave you the mass of the carbon and the hydrogen. So the first problem-solving strategy you should utilize is to realize that since there's only 3 elements that make up the 5-gram sample, that the additional mass must be coming from the oxygen. So if I subtract 5 from the other 2, the leftover mass must be the oxygen mass. That's the only reason why they give us 5. Very often I start to see students want to put down 5 down here, but we don't. The 5 is just to allow us to figure out that all of the masses of the elements should add up to 5 if it's a 5-gram sample. Okay? Now, dividing each of these gram quantities by each of the elements' molar masses gives 0.1098 moles, 0.1644 moles, and 0.2197 moles. The 0.1098 moles is the smallest number, so we're going to divide all of them by that number, and we get 1. We get 1.497, which really closely rounds to 1.5, which is 1.5, and 2. So we end up getting a fraction of 1 carbon, 1.5 hydrogens, and 2 oxygens. So we need to multiply by 2 to get that into the simplest whole number formula, which ends up being C2H3O4. Now, students oftentimes think that they are done, but this is still just the empirical formula. It could be the answer too, but we have to do one final check, and that is we now have to take that formula, we have to add up 2 carbons, 3 hydrogens, and 4 oxygens, and we get a mass of 91 grams per mole. The molar mass of the compound is given at 182. So 182 divided by 91 gives me 2. It's got to be 2 times heavier, but it has to keep the same ratio. So multiplying all the subscripts by 2 again, we get 4 carbons, 6 hydrogens, and 8 oxygens. And that is the molecular formula. This is about as complex of a problem as you will see on the test, but it's one that you should be able now to be able to do. Please do the homework problems on the next 2 pages. There are other ways of doing these problems where you could utilize the 5, but this is the most common way that most of my students do it. But if there's a way that you can do mathematically and show support of it, I'm fine with that, but this is the way I recommend most of my students do these problems. So now go ahead and do the next couple of pages as extra additional practice. The answer keys are online, and then you can check your work over, and that really concludes the end of this unit. You'll have a quiz off of percent composition, empirical molecular formulas this week, and the next week it's all about getting ready for the test. And that'll take us to the spring break and the end of quarter 3. Thanks so much.